And this is actually a good reminder not to mix the integration tests that we rely on an external state somewhere, let's say database, and the unit test that we should actually self-contain dependencies or create like a state for every single test separately.
That's a very good point. And there's another thing we should desire about tests, isn't there? That they should be idempotent. In other words, if they do alter the world in any way, then they should clean up after themselves and leave the world the way they found it. You know, if the test creates a file on disk as part of what it does, it should delete the file. You know, you don't want to, like, every time you run your tests, you get more and more cruft landing in your repo, which you then have to delete. And I do see that sometimes. And similarly, you know, whatever you change in terms of global state, or, you know, there almost always is some irreducible global state, isn't there? Like if you have a database, you know, that's effectively your global state store, and you could imagine a test that's like create person, you know, create Mrs. Smith, and then that's it, and Mrs. Smith is just left in the database, and the database just gets bigger and bigger and bigger. We could take two approaches here, couldn't you? You could either nuke the world before you start, just drop table users, you know, and then do your creating. That's a little bit risky, because what if you accidentally connected to a prod DB? I mean, you laugh, but that has happened. I'm sure we've all read on Reddit and Hacker News about some poor intern or, you know,
oh yes, it was
junior.
last year or 2 years ago.
Yeah, well, it happens about once a year, I think. You know, poor old junior developer sits down and say, you know, the boss says, right, first thing you do is run the tests, and they run them, and they say, you know, it's boss, it says here dropping production database. Should that be happening? You know, and then the next thing is they're posting on Reddit explaining why they got fired, quite unfairly in my view.
Exactly, and the test is green.
Yeah.
Yeah,
Yeah, that's the saddest part, isn't it? So I think anytime you want to do some operation which is potentially risky, some engineers would say, let's see if we can mitigate the risk, you know, make sure that it doesn't cause problems. But an even better solution would just be to not do that, wouldn't it? Just never do anything potentially risky. Then you don't have to worry about whether your mitigation is correct.
yeah, exactly.
So don't nuke the database, just create a person and then delete exactly that person. So you ensure that the world is left the way you found it, but you didn't blow away anybody else's data. It's
Exactly.
just
Yeah.
being
Much safer. Much safer.
being a good citizen, isn't it? So it's surprising how much of this there is when you think about tests. Really, isn't there? Tests seem like such a simple idea, but when you actually come to writing real tests for real code, you find there's all these sort of little complicated issues that you have to think about.
And possible dangers.
Yeah, very much. But it's almost always better than not having tests at all.
Okay, so we have the lender state struct here. So this is our, looks like it's our new desired state after some operation. Let's, I think, and then, yeah, on the line 74, we are calling the update world on the new game object. So I suppose this is this updating the internal state of our game. And
it's basically like do physics.
Yeah.
You know, apply Newton's laws. We could use general relativity here, but it's, you know, probably not necessary at these energy densities and velocities. And it's, you know, they don't, in fact, for real space missions. They just use Newton's laws. Did you know this?
Yeah.
It's apparently, you know, good enough. Although Einstein extends our understanding of gravity. It's very much in the low down decimal places. So not likely. It's the sort of thing you notice, with the mass of a star or a black hole or something, or velocities close to the speed of light. Not the sort of thing that is going to affect your moon landing. So it really is very, very simple. And when you see the code for update world, you'll be like, oh, really? It's that easy? So yeah, it's effectively like, update the world one tick, and we know the initial numbers, so we know what the numbers should be afterwards.
Yes, so we have on 68 line defined this state after the update, and then we are checking actually this state. We are assigning this state to got, and then we have on line 76 till 77 verification if the struct looks basically the same, and this is really, really nice way and cleaner way to comparing the entire struct.
Yeah.
Using this CMP package instead of actually looping through all basically the fields in given struct and comparing them one by one.
Yeah, exactly. We could use reflect.DeepEqual from the standard library, but it's not as powerful, not as convenient in many ways, and it doesn't have diff. So often what we really want to know is the diff, isn't it? If you have a struct with 100 fields and all of them are correct except for a couple in the middle, you just want to see what's different, because if you print out both structs, which is what people usually do, that's really hard. It's just your brain is not good at spotting tiny differences in large amounts of data, is it?
Yeah, especially if you have large structs. So I was using in the past the DeepEqual comparison, but since I moved actually to CMP package, it's much easier to interpret the error results on the screen.
Yeah. Yeah, that's right. So that's great. So, and it's, all my tests always sort of follow this pattern, and it's what I try to encourage other people to do. And on one consulting project, we were sort of refactoring a bunch of tests, and the person was saying to me, John, if you had your way, all of our tests would just end up being like if want not equals got. And I was like, yeah. What's your point?
Exactly. That's the simplest way to do this.
Yeah, that's the world I want to live in, because I don't want to have to, I don't want to have to cognitively figure out how is the test working, what is the test doing, and then also what is the behavior of the program that it's trying to test. I want the test to just be a known standard thing, that it always looks like this. I define my what, define my want, I get my got, and then just compare them. That means I don't have to think about it when I look at it. I'm just like, yep, standard test. I can focus on what it's actually testing. So that's great. Very nice test review. Thank you. Should we take a look at the package?
Okay, so CMD or Lander? Or Lander?
Let's look at Lander. It's a lot
Lander,
smaller.
Okay. Okay, so here we go. Package Lander. So we are defining, I see the type state. So this is the state of the game. All four variables are the float 64. Then we have the game struct, which is basically our state.
Yeah, by the way, somebody asked me about float 32 the other day. We were considering some numeric field suitable for receiving a JSON number. And they said, can I just put float? And I thought, yeah, that's right. There should be a type called just float, shouldn't there? Like there's a type called int, for when you don't care about how many bits there are. But unfortunately, we don't have that. We have float 32 and float 64. And he wrote float 32 because he's sort of thinking like, well, it won't be bigger than that. So let's save bits. Sort of understandable, isn't it? We as programmers, we don't want to waste CPU cycles or memory. If we know that the number is going to be small, we can use a fairly narrow data type to represent it. But I think that's a mistake, because I saw a news story yesterday about, you might have seen this, the Berkshire Hathaway investment company, Warren Buffett's firm, is their stock price has risen so high that it's actually causing problems for the Nasdaq
Oh
because
no, didn't hear.
they use 32-bit integers to represent the stock price, not in dollars, but in, I think, 10,000ths of a dollar. And the stock price has reached the level at which it's overflowing 32 bits. So, there's a lot of amusing snark about this. But it does just sort of make the point that, like, if you find yourself saying 32 bits should be enough for anybody, then just think, actually, you know what? The machine itself is 64-bit. The data bus is 64 bits wide, the CPU is 64 bits wide. We're going to pay the penalty of shuffling those 64 bits around anyway. So let's just use them. We're not saving anything by leaving half the bits on the table.
And this actually story it's a great example that engineers should have in mind, that actually the engineering decision can have and has actually huge impact on the business that they work for. So we are talking about, let's say, float 32 for float 64 here, and then at some point suddenly, for example, we can cause some disruption of the stock exchange.
Yeah. Yeah, or a space probe crashes, or people can even lose their lives as a result of this sort of thing, which would be a sad position to be in as a programmer, wouldn't it? So, I think it's always worth asking yourself, anytime you have to make a decision like this, again, just err on the side of being generous. Just make it twice as big as you think it needs to be, or 10 times as big. Who cares, right? Just buy a bigger computer. It's quite interesting to me that, when you read about the development of computers and operating systems in the 60s and even the 50s, a computer was such an expensive machine per bit, if you like, that people absolutely were focused on saving every nanosecond and every bit and byte. And sometimes you had these hugely complex programs only because they're so desperate for every bit of memory. And that really isn't the case anymore, isn't it? I mean, I can remember even in the 90s working for a palm top manufacturer, Scion, making sort of pocket organizers. These things have, it's a little flash memory device which has, some low power ARM processor, little calendar application, word processor, email, basically an iPhone, but before those were invented. And those people were geniuses. The programmers there were geniuses at getting every last bit out of the machine, because it only had a certain amount of ROM, and that was full always. Every byte of ROM had been used. So when they wanted to add a new feature to the calendar or something, repeating appointments, let's say, they would work out, I think we can do this in 37 bytes. But we don't have 37 bytes, so we need to refactor everything else across the entire operating system to try to save 37 bytes so we can squeeze this new feature in. And that's what they did for every new feature. And they always managed it, which is amazing.
Mm-hmm. That was really engineering in terms of actually getting from the hardware as much as possible.
Yeah, absolutely. And if you read about the original Elite, which I suppose is sort of another ancestor of this game, that was the case there, because they were working on a 32K, I think, BBC Micro. And that was, obviously they entirely filled those 32K with code. And so anytime they wanted to add something, they had to try and figure out how to squeeze it. And I think they had got to the point where the game was complete, but you only had one galaxy. If you know Elite, you have multiple galaxies that you can hyperspace between. And they really wanted to add extra galaxies, and I think it was the day before the launch. And, of course, the publisher said, "What are you thinking? Don't tinker with it now. We're about to ship it." And they said, "No, we can do galaxies." and I think we can do it in about 12 bytes or something in the end, which was, which is absolutely insane because what they were doing was procedurally generating the entire galaxy from a single seed number, which is very
Mhm.
impressive in itself. They're using a pseudo-random sequence based on Fibonacci numbers, which is a very cheap way to do it. And you know, the entire galaxy comes from just one number, and what they would do would just pick numbers and see if they produced interesting galaxies, and
Yeah.
they kept their favorites. And some of them, because the planet names were auto-generated too, and some of them were accidentally rude, so they had several ones where it was a really promising galaxy until they came across some planet which had an obscene name or something. They said, sorry, you can't use that one. And of course, you can't just edit the planet. You have to
Yeah.
just start with a whole new galaxy. So that's uh,
That's actually, speaking about the hardware, right? So that's actually good and great, I would say, about the Go, that we are dealing not with another virtual machine. We are dealing basically with the real hardware in this
right.
language. Yeah.
Very true, yeah. And I know it's a huge digression, but that's okay. It's my show and I can say what I want. But basically, to sort of underline the
Yeah.
point, that basically that's not the case anymore. Memory is extremely cheap. I can't even remember how many gigabytes I've got on this Mac, which is itself very old, but I certainly
Yeah.
never use them all. I don't find myself running out of memory, certainly not in Go programs. So we
But
can,
certain Go programs that right now Go becomes the more and more popular actually as a language for the IoT devices or even also microcontrollers.
right.
So we are more or less we will need to think about the real hardware if we want to actually start developing more Go programs on the small devices, edge devices, right?
That's very true, and I think that would be awesome. I mean, I've never done any embedded system programming, but if I did, I'd certainly want to do it in Go, and there's no reason why not, is there? As you say,
Yeah.
it's relatively close to the hardware compared to some languages. And
Yeah.
there's a special version of Go called TinyGo. You might have seen
Yes.
this, which is
Yes.
especially
Yeah.
for
Yeah.
that. And I think it's not a complete implementation of Go because it turns out there are certain things which are just really awkward on embedded hardware, and it doesn't do them. But that's okay because the subset of Go that you can write is absolutely enough to write a washing machine controller or whatever you want,
Yeah.
blink some LEDs or whatever. So that's great, and I would like to play with that at some point. So and of
That's
course, since we're in a space context, um, space hardware as well needs code, and I remember seeing recently that the Mars helicopter Ingenuity, when they
mhm.
did some tests on that, they found it wasn't quite right, and they needed to fix some stuff before the actual first flight. And obviously, you can't go and twiddle the nuts on it. So it's all software, in fact, firmware with that machine. So what they did was they basically reflashed it. You know,
Uh-huh.
they fixed the firmware, uploaded a new firmware, and flashed it just like you'd flash your broadband router, um, with presumably the same worry while it's happening. They're like, is this going to work, or have we just bricked this machine? Thankfully, they didn't. And it took an awful long time to upload that firmware, apparently. The bandwidth between here and Mars is not great. Um,
Mhm.
it's, something like a few kilobaud, a few kilobytes per second. Um, like, not quite as good as an old school acoustic coupler modem that I used to use back in the 90s. So there you go. Um, so yeah, so you certainly would not want to be programming stuff like that in machine language because it's just too easy to get wrong. By the same token, you wouldn't want to be using something like Java, would you? It's
Yeah.
no insult to Java, but the JVM is quite large, and
Yes, exactly. Yeah.
you'd have to port it to whatever SoC you're using on that space hardware, which would be a job in itself. So yeah, I don't know if there is any Go code running in space. That would be amazing, wouldn't it?
Mhm.
Perhaps we can find out and report back.